Hello students, welcome back to our next lecture on environmental modeling and simulation. We'll continue our discussion on bifurcation and especially with the example that we covered in the last lecture, which is the example of a fishery model. So, our fishery model after we did dimensional scaling looked something like this. df by d tau is equal to f into 1 minus f minus h. If you want a revision on what f and h are, consult the previous lecture. What we also managed to do was understand how the bifurcation is happening and the kind of bifurcation that we are seeing here. And we saw saddle node bifurcation. So, I will quickly draw the phase portraits again. We saw that if we make a phase portrait like so, and this is let us say f square, when h is positive, there are no fixed points, and as we reduce the value of h, I am going to use a different color for it, eventually there will come a critical value of h at which the line will be tangential to the curve. Finally, beyond this value of h, as h continues to reduce even beyond h critical, the line will intersect the curve at 2 points. The first fixed point and the second fixed point. We also figured out that the first fixed point was an unstable fixed point, while the second fixed point would be a stable fixed point. Now we are going to make the diagram that shows how the fixed points are changing with change in parameter. So, let's change the parameter on x axis and the fixed points. I am showing the fixed points by this symbol. When h is positive, there are no fixed points. So, when h is positive, we do not have any fixed point. So, the second and the first and the fourth quadrant will stay empty. For a particular critical value of h, when h is still positive, h critical, one fixed point appears. This is when the line and the curve are tangential to each other. Now, as we keep reducing the value of h, two new fixed points appear. The positive fixed point is stable, the negative fixed point is unstable. And this is a quadratic equation, so it will look something like so. So, this is how our bifurcation diagram looks like. Clearly, this is a case of saddle node bifurcation. Now, how do we interpret it? First, let us find out the value of h critical. Okay, to find the value of h critical, we need to meet two conditions. First, that the line and the curve should be tangential to each other. They should intersect each other at exactly one point and their slopes should be same. So, if we open this bracket, we get df by d tau is equal to f minus h, we are treating it as a line, and minus f square is our curve. So, f minus h should be equal to f square. This is the condition that they meet at one point, they intersect at exactly one point. It is not an intersection, it is just tangential contact. And the second is that the slope is same. So, if we differentiate it by d by df, they would be same. So, let us do this. Here we get 1, 2f, f is equal to 1 by 2. So, if we put this information here, we will get h is also equal to 1 by 2. So, we get our h critical is equal to 1 by 2. And the value of f at this point is 1 by 2. Okay. So, this is our fishery model. Now, one thing we know very clearly that if we increase the rate at which we are fishing above a certain value, then what will happen? Let us look at the phase portrait. Let us zoom in into the phase portrait a little bit more. So, we have df by d tau here, f here. This is our f square, because remember df by d tau is equal to f minus h minus f square, and this is our f minus h. So, here for h critical, the line and the curve are tangential, they meet at exactly one fixed point. And if you notice the kind of the fixed point this is, the curve is above the line, it is an unstable fixed point on this side, and here again the curve is above the line, so it's moving, its df by d tau is going to be negative. So what we see is it's attracting on the right side and repelling on the left side, half stable, half unstable. However, just looking at this phase portrait informs us that no matter what number, what f we are starting with, now f is not number of fishes, remember we have dimensionally scaled the system. No matter what our initial f is, the number f will keep on reducing. And since we are dealing with actual number of fishes, we know that because f is equal to f by k, right. So no matter how close or away we are from the carrying capacity, eventually the small f will keep on reducing. Since k is constant, f will reduce. Basically we are driving the fishes to extinction, except when we are starting at a value of f larger than half. Because on right side of this, except in one situation. So notice that here h critical is equal to half, f is also equal to half. If we are starting, if our f initial is greater than or equal to half, basically the initial number of fishes, because this is equal to f by k, initial number of fishes is greater than or equal to carrying capacity by 2, then the number of fishes will continue to reduce until they reach this fixed point. The moment they reach this fixed point, they have reached the fixed point, they will stop moving. However, if the f initial 1, f initial 2, if the f initial is less than half, if they are starting at a value less than half, then small f will keep on reducing until small f becomes 0, which means if we are starting with less than half of the carrying capacity and our h critical, our fishing rate, h given by h divided by kr is equal to half, then we will drive the fishes to extinction. Now let us look at what happens when we have two fixed points. So this is our curve, f square, and this is our line. H is in this case clearly less than 0, but it does not have to be less than 0. What it has to be is less than half. H is less than half, it is intersecting in two places. One is here, the other is here. We already went through this. On left side the curve is above the line, so df by d tau is going to be negative. Here it is going to be positive, negative, stable, unstable. So if h is less than half, if we are reducing the rate at which we are fishing h less than half, which is equal to h by kr less than half, which means h is less than half of carrying capacity and growth rate of fishes. If we are limiting our fishery to less than this number, then we have two fixed points. The negative fixed point, which means we have already reached extinction, is unstable, and then here the stable fixed point is a positive one. What it means is, as long as our fishing is limited to this particular number, it is not going beyond it, no matter what our f initial is, we will always end up with this number of fishes, this second fixed point. So if you are starting with a smaller f initial, look, the flow is towards right side, number of fishes will increase until they reach here, as long as fishing is contained to this. What happens when we go at a fishing rate much higher than this? So again, curve, now h has gone beyond half, which means the rate at which we are fishing is bigger than carrying capacity into growth rate divided by 2. Now what is happening here? The curve is always above the line, df by d tau is always reducing, which means no matter what our initial fishing population is, Even if we start with a pond that is full of fishes, eventually we are going to run out of the fishes. We are going to drive them to extinction. So if you look at this model, just by even before we calculate, as long as we understand the conceptual fishing model, we are able to write a very simple mathematical model for it. We can already tell that as long as fishing is contained less than or equal to the critical value of half, we will have fishes in the pond. We won't run out of it. Now, this is not a perfect model for many reasons. One, we are oversimplifying the fishing rate. We are saying it is constant. That's not true. The rate at which we fish typically is dependent on multiple parameters, including the number of fishes in the lake. So, if we improve our model, we'll be able to get a more clear estimate of how much and up to what extent we need to limit our fishing. Okay, so this was our fishery model, and I wanted to give an example how we can use our qualitative analysis to understand how the system is working, how to even without solving and simulating anything, we can get an idea at what rate we should stop our human activities, which is very important for impact assessments and deciding policies around projects. Okay, now what I'm going to do is I'm going to introduce imperfection in the model. So if you remember, the last kind of bifurcation we studied was pitchfork bifurcation. And one of the things that I told you about pitchfork bifurcations is that they work with systems that are symmetrical. So the example that we had was, what if dx by dt is equal to rx minus x cube? So this is a case where we'll have characteristically decay. We'll have characteristic slowing of decay. So because the term that will decide the stability of the system is minus x cube, so we'll see that around the critical value, as the parameter r moves around the critical value, x will slow down towards the fixed point. We have already gone through this, and remember, this is a symmetric system. But what happens when we violate the symmetry of the system? So let's introduce an imperfection in the system. The imperfection is h. Now, you might ask, why is it important to introduce imperfection? Let's take a very simple case of simple pendulum, right? It is a symmetric system. No matter whether you displace on the left side or on the right side, the motion will be quite similar, which is oscillate around. And if it is a perfect system, it will oscillate until an external force stops it. However, on Earth, when we oscillate simple pendulum, friction, losses, atmospheric drag, all these forces resist the movement of pendulum, and the pendulum is a damped oscillator. That damping is the imperfection which is introduced in it. And imperfection is extremely important. In nature, we rarely see perfect oscillators, or we rarely see perfect bifurcations. There's frequently some variable, some confounding variable that will introduce imperfection. Imperfection is also very important because we see that when we have phenomena that emerge from these complex environmental systems, such as outbreak of a new disease, or insect outbreak, or forest fires, or landslides, it is typically these tiny imperfections that are working in the background that cause these phenomena to emerge. So what I want to do is I want to talk about what happens when we introduce imperfection to pitchfork bifurcation, and then I want to use this to model insect outbreak. But I must tell you at the very onset that outbreaks of insects or sudden increase in the number of a particular population, a particular species, is not limited to imperfections, even though imperfections are very important. Even saddle node bifurcations can give you sudden outbreaks. Okay, so what happens when we are dealing with an imperfection? Rx minus x cube plus h, we are going to do bifurcation analyses. Now we have two parameters and we are going to vary both of them. So let's get started. Step 1 is to find the fixed points. Once again, we are going to take the graphical approach. So clearly this is a very interesting cube. So let's separate it. We can split this system into a line and a cube. So we have Rx plus h, which is a line, minus x cube, which is a curve. So dx by dt here, x here. Now Rx plus h and x cube, these are the two curves that we are going to draw. X cube looks like this: sudden increase, sudden decrease, rapid increase, rapid decrease. Rx plus h is a line with slope r and intercept h. So let's look at the scenario when h is positive, and we'll start with r being positive. Okay. So h is positive, intercept is positive, r is positive. So we might have one intersection here, one fixed point here. Let's look at the stability of this fixed point. On left side of this fixed point, the line is above the curve, which means dx by dt is positive, the flow is towards right side. On left side of this fixed point, on the right side of this fixed point, the curve is above the line, which means dx by dt is negative, which means the flow is towards minus infinity. So this is a stable fixed point. What we are going to do is we are going to keep the imperfection constant, and we are going to keep the imperfection constant, and we are going to vary the r, the slope, and then we are going to reverse it too, so don't worry. So this is our cube. This is very convenient because one function is independent of the parameter, so we can always keep it constant. We just have to vary the line, the intercept and the slope of the line. So we are keeping the h constant, we are varying the r. So we keep the intercept constant here, h, same h here. Now let's make r equal to 0. Again, you see no difference, only one fixed point, it's a stable fixed point. Okay, we can go one step further here, and we can make r less than 0. Again, you see only one fixed point, so let's keep varying the r. I made r very large, again one fixed point, and then eventually we can make an r that intersects, and eventually we can find an r, so I'm looking for another color, that will be tangential to the curve on left side and intersect the curve on right side. So now we have another fixed point that has appeared. Okay, let's look at the first fixed point, the stability of this fixed point, stability of the second fixed point. So what I'm doing is I'm changing the r, I'm keeping h positive, keeping the h constant. Now here on the left side of the first fixed point, the line is above the curve, flow is towards right side. On the right side of this fixed point, the line is again above the curve, so the flow is again towards right side. Now here, second fixed point, on the left side, line is above the curve, flow is towards positive infinity. On the right side of this fixed point, the curve is above the line, flow is towards negative infinity. So clearly this is a stable fixed point, this is a half stable, a half unstable fixed point. Okay, let's keep changing the r, keeping our h constant. So for the same value of h, we can now have an r that is no longer tangential on the left side, but intersects on two fixed points. So now we have three fixed points, fixed point 1, 2 and 3. Students, I encourage you to not just watch me do this, but do it yourself, because only when you do it yourself, even if you are listening to me do it, just following, just copying, taking notes, that is when things will start clicking in. Otherwise, it is, you need to do it yourself. This, I don't think it will be very helpful. Okay, so we have three fixed points here. Let's very quickly find their stability. On left side of the first fixed point, the line is above the curve, which means flow is towards right. Here, flow is towards left. Again, the flow is towards right, flow is towards left. So we see the first fixed point is stable, the second is unstable, the third fixed point is stable. This is very similar to what we have already seen, right? Now let us vary the h. So we are going to keep r constant. We are going to start with r that is positive. And we are going to vary the h. So we'll start with an r that intersects at three places, which is where we left last time. So here we have one fixed point here, another fixed point here, stable, unstable, stable. Now we're going to vary h. What happens when I reduce the h? So as I reduce the h, this intercept comes down towards the intersection of the axes, and I still have two fixed points. And if I keep reducing the h, there will come a particular value of h where there will be only 2 fixed points left. So, this is our H critical for the same value of r, right. So, at this H critical, the line is tangential to the curve here and it intersects here. If I keep reducing H even further down, then there will be only one fixed point. So, if I am reducing the H, the 2 fixed points collapse into one fixed point which disappears. Now, let us go in the other direction. In the other direction, if I increase the value of H from here, which is the original one, there will come a time when the line will be tangential to the curve here. So, we have collapsed 2 fixed point into one and we have one fixed point here, until if I keep increasing the H, then there will be only one fixed point on the right side, which is positive. So, you see, as you vary H, keep your r constant, there is fixed points are appearing or disappearing. As you keep the H constant and vary r, fixed points are appearing and disappearing. So, when you make your bifurcation curve, to understand the kind of bifurcation that is happening here, you will have a 3D map. A map where we can plot r and H on 2 axes and our fixed points on the third axis. Before we go there, what I want to do is I want to make bifurcation curves when we are just varying r, when we are just varying H. Okay, so what we will do is we will first make the curve for this analysis where we kept the H constant and varied the r. Okay, so here H has remained positive, but we have varied the r. So, let me clear up some space. So, in our bifurcation curve, what we are going to do is draw fixed points on y axis and draw the parameter that we are varying, not the one that we are keeping constant r, on x axis. Here H is greater than 0. So, we also have to do for H equal to 0 and H less than 0. H equal to 0 is same as the pitchfork bifurcation that we have done, H less than 0, different ball game. Alrighty. So, what happens when H is greater than 0 and r is positive, r is greater than 0? Up to a certain value until it reaches H critical here, what we notice is that there is only one fixed point and it is a stable fixed point. As r changes, as r increases further, so we up to a certain value r critical, up to a certain value of r critical until we reach here, this is r critical. There is only one fixed point, right? This is a fixed point and it is a stable fixed point. And as we change the value of r critical, as we increase the value of r critical, another fixed point appears. This is a negative fixed point. So, it is appearing here. At r critical, we have a positive fixed point, which is stable. And as r increases, another fixed point appears, which is a negative fixed point. This is a half stable, half unstable fixed point. As r increases further, as r increases further, this negative fixed point splits into 2 fixed points. The smaller one is stable and the bigger one is unstable. So, what we have here is smaller one a stable fixed point, bigger one unstable fixed point. This is what is happening here. Now, as we notice that as we are increasing the r, the third fixed point is also slowly increasing. So, we know that this stable fixed point is also increasing. On the contrary, as I am reducing the r, if I reduce the r, this fixed point on the left side, this one disappears, and this particular fixed point, which is the only fixed point left, the stable fixed point, starts slowly progressing until r is equal to 0, it will be a small fixed point. So, here we have a positive fixed point, and then as r becomes negative, this fixed point slowly reduces until at minus infinity it becomes equal to 0. So, at minus infinity it will approach 0. So, when H is positive, you are varying your r, this is your bifurcation diagram. What kind of bifurcation it is? Is it exactly a saddle node bifurcation or is it a pitchfork bifurcation? See, it cannot be a saddle node bifurcation purely, even though here it has some features of saddle node, because there is one fixed point which is always there and it never changes its stability, which is a marker of pitchfork bifurcation. Okay, we also need to do H less than 0. So, let us do that. This is our cube. We are going to keep H negative and we are going to vary the r. So, remember our original equations were this: Rx minus x cube is equal to H plus H is equal to This is our original equation, remember that. So h here is negative. So the line that we are going to draw, rx plus h minus x cube, this is the line. H is negative, so the intercept of the line will be negative. So we are dealing with a negative intercept. Now let's vary the r. So let's start with r equal to 0. This is r equal to 0. One fixed point here. Yeah, so now we're dealing with h equal to less than 0. So one fixed point, stability of the fixed point. On left side, line is above the curve, which means flow is towards right. On right side, curve is above the line, flows towards left side. This is a stable fixed point. Now let's increase r. As we increase r, eventually there will come a time when the line will be tangential on the right side in the first quadrant. New fixed point appears. This fixed point moves here. So let's look at, I'll change the colors to make it less confusing. So here we have a new fixed point here, another fixed point here. Let's look at the stability quickly. The first fixed point on left side, line is above the curve, flow is towards right side. Here the flow is towards left, so this is clearly a stable fixed point. Here, in the second fixed point, on left side the curve is above the line, which means the flow is towards left. On right side the curve is again above the line, which means half stable, half unstable. Let's change the color again. Now we are going to change r more, increase the r more, and we'll reach a situation where we'll have 3 fixed points. Okay, 3 fixed points, let's draw them. One is here, one is here, and one is very close to this, so let's just overlap them. Okay, I'm using different colors because I expected some kind of overlapping to happen here. Okay, first fixed point here. On left side, once again, the flow will be towards right. On the right side, the flow will be towards left, so this is a stable fixed point. Let's look at the second fixed point here. On the left side, the curve is above the line, so the flow is to the left. On right side, line is above the curve, the flow is towards right. This is an unstable fixed point. Now on the third fixed point, on the left side, the line is above the curve, so the flow is towards right. On the left side, the curve is above the line, so the flow is towards left. This is a stable fixed point. Now we are going to draw bifurcation diagram. It's a very lengthy process and you'll have a question in the exam if you choose to write it. Okay, now we are going to draw the bifurcation diagram. This is for when h is less than 0. Y-axis we draw the fixed point. On x-axis we draw the parameter that we are varying, which is r. When r is equal to 0, we had one fixed point. It was a negative fixed point and stable. So when r was 0, here we had one fixed point which was a negative fixed point here. Now what happens when we increase the r slowly? So we increase the r, we moved here in this direction. There came a time when a new fixed point appeared, which is a positive fixed point. A new fixed point appeared. What happened to this fixed point? This fixed point very slowly started increasing because it's increasing but increasing very slowly. So here at r critical, a new fixed point appears which is half stable, half unstable, this one. As we keep increasing r even further, this fixed point, the first fixed point, very slowly, stable fixed point keeps on increasing. This new fixed point, saddle node that has appeared here, also splits into two. The larger one is stable, the smaller one is unstable. Now what happens when r is negative? So let's very quickly take a look at it. When r is negative, we have one fixed point. And that fixed point collapses into 0. It's a stable fixed point, collapses into 0 when r approaches minus infinity. Something like this. So this is our bifurcation diagram. When we are keeping the h constant, h greater than 0, h less than 0. And this is how we are just varying the r. We have done what happens when we keep r constant and vary h. In the next lecture, I'm going to draw bifurcation diagrams for this, both positive and negative r. And then we are going to combine them together and draw. And I'll not draw it, but I'll show you how it looks in 3D. And then we'll look at insect outbreak model. This is all for today. See you in the next lecture.